the audio. The audio was off last stream, I think. Quite annoyingly. It looks to be on, at least OBS says it's on. I'll come back to the what's still, I think, the most satisfying view in the entire computer, which is obviously, if you've not seen this computer before, this here is just, well, this is a small corner of the RAM. There's 16 memory addresses in each one of these data tranches. Um, so, and then there's 16 of these going that way. And then theoretically there's 16 of these connected to that bus over there going off in that direction. For a theoretical total maximum of sort of 8,000 bytes of memory, so 8 kilobytes of RAM. Yes, obviously that's just the beginnings of the CPU over there. Again, if you're just joining in, what I'm actually doing here is, this is sort of the control center for the CPU, which is going to be built out here. This is obviously the main CPU data bus. Then I've got my system, my very messy system here to connect in the logical operators. There's a reason for that mess. It's not the most aesthetic design in the world. And this here is the binary adder at address 000. Obviously, this is all a bit empty, and that's because I have been building. Essentially, I've decided that I will build all of the logical operators like the binary adder here over there in essentially the unused empty space, and then once they're done, I'll copy and paste them into the CPU. Because at this point, the CPU is somewhat modular, at least in terms of adding on these. I can just use this universal connector here and copy paste it. And of course, once I've done all that, I will need to sort out all of the timing and the control circuit over here. But hey, that's a problem for me next year. Yeah, it's going to take a while, especially with only 2 to 3 hours put in a week. Now, last stream I had some interesting things to say. Unfortunately, the audio was off. So what I'm going to do this week is I'm going to pretend that I didn't say anything last week, and I'm going to say everything again this week. And pretend it's all new and novel. So started with a bit of revision of Weil equation, which is well, it's a quantum mechanical equation. It's not, sorry, it's a quantum field theory equation. So what this means is it's invariant under Lorentz transforms, which is the special relativity transformation rules. So the equation is invariant under that. But it transforms under special unitary group transformations, I believe. Or is it SL2? Either way, it transforms as two component spinner. So it's so what the Weil equation is it's an equation for a massless fermion. So it's the equation for, if there was a particle like the electron but it had no mass, then that would be the Weil equation. Potentially neutrinos, but neutrinos have mass, so they don't obey the Weil equation. They are Majorana equations, which is essentially is a Weil equation with a mass term, so it's sort of the Weil equation. Also, if you're wondering about the pronunciation, Weil is spelled W-E-Y-L. That's just how I'm pronouncing it. I have no idea if that's accurate. So the equation has, so obviously firstly, the equation is a first order differential equation, so and it's the time component is so both the time component and the spatial component are first order, which is one of the reasons why it can be Lorentz invariant. Um, sorry, just talking about this is making me forget what I'm up to here. So I did all of this, which means I need to. Oh yeah, in case you're wondering what I'm doing right now, this here is the bit shifter, which will then be fed into a series of addition units. But yes, so the Weil equation is a first order equation with a left-handed and right-handed um, chiral pairs. So there's essentially two versions of the Weil equation, one of which is left-handed and the other one is right-handed, and essentially this corresponds to the sign. So every wave equation has like the derivative with respect to time, and then it's either you subtract or add the derivative with respect to spatial coordinates, partial spatial derivative, and then obviously that the sum or the subtraction of those two either is summed to a constant or it's summed to zero, or in some cases it could be summed to a further driving force. But so the Weil equation, like if the sign of the um, spatial coordinates is negative, that I believe is the right-handed representation. Um, I think that's correct. It's not super important. I mean, it's super important if you do the math on paper, but conceptually it doesn't matter. You have to remember is it just switching the sides, which is the handedness of it. And that corresponds to it comes down to the Minkowski. It's related to the Minkowski metric, which is the sign of essentially special relativity space time. Essentially, Lorentz transforms keep preserve the square of the time minus the squares of all the spatial coordinates, which is where you get the Minkowski signature from. But and obviously it's a flat space time, so those are all um, set to 1 or minus 1. But anyway, what was confusing me was why the handedness of it, which corresponds to which way it transforms in the Lorentz. So the Lorentz group has a left-handed and a right-handed representation, right? And the handedness of the Weil equation corresponds to which representation of the Lorentz group it transforms under, which might not make a whole lot of sense because you'd think everything would transform under either one of those representations, but whilst that's sort of technically true, it's not really true because it's because of the way the basis works. Essentially, if you have, it's a bit tricky. This is basic shit. I should be able to explain it. So the Lorentz. So essentially, if I understand it correctly, you can represent a vector in Minkowski space either with a left-handed basis or a right-handed basis, and it will be the same vector. Now, if you maintain the condition that that vector is the same vector, in either representation, as in once it's translated into real space, whatever that might be, that those two vectors are the same. Essentially, if you want them to translate the same into vectors that are still equivalent once you've translated them, you have to use either a left-handed or right-handed Lorentz representation, respectively. Whereas if you just use the one for each of them, they won't transform correctly. Is, I believe, the correct understanding of that. But I have really struggled with this particular aspect of the math, so it's quite possible I got that wrong, if not very likely. Um, but and again, so changing the basis involves essentially switching the signs of the basis vectors, switching an odd number of signs in the basis vector. So if you add for example 1 minus sign, you switch the basis, or if you add 3 minus signs, you switch the basis, or whatever. As usually it means you switched the spatial coordinates from positive to negative side. So anyway, what wasn't immediately clear to me about the Weil equation is, why is it that the chirality of it, which is a function of which group it transforms, which Lorentz group it transforms under, why is that tied to why it spins? Because fundamental spin of a particle does represent a real concept, right? So it represents essentially it represents a vector that is real and does spin. Well, as real as anything can be in that sense. So why does the angular momentum of the particle, the spin of its spin, and why does that depend on which group it transforms under in the Lorentz group? And if you look at the Weil equation, you dig into it. Well, firstly, right, a wave function can spin because, so essentially, if you have a wave function that's defined in three-dimensional space, you could either have a scalar wave function, which means you put 3 coordinates in, you get 1 value out, or you could have a vector wave function, which means you put 3 coordinates in, you get, it could be anywhere from two values to an infinite number of values, right? But normally it would be you put three values in, and then you get 3 values out, and one of those values is 0, and then the other 2 values are cosine of x and sine of x. And because cosine and sine are at 90 degrees out of sync, that leads to a vector that is rotating in a plane as the sine and cosine move through their phases, right? And obviously the third vector axis is set to 0, so that's why it's in the plane. And usually the third axis is the axis of progression of the wave. So it's spinning, the wave is spinning around its axis essentially. With the Weil equation, you have the Weil spinner solutions, and the Weil, obviously spinner is just a complex. It's just a complex number really, but in this context, what it is a complex exponent, which is expands to a sine and a cosine, where the sine, so essentially it's cos of, let's say it's cosine of x minus I sine x, essentially. So you have a real cosine term and a imaginary term that's 90 degrees out of phase, the imaginary sine term, right? So you have that, and then with the Weil spinner, it's a 2-component spinner, so it has 2 of those imaginary waves, right? So obviously the components are there for it to spin as you'd expect. Obviously, it being a complex number makes it difficult to visualize and think about. You know what's really difficult to visualize and think about? This stupid computer. Um, uh, and essentially, did I didn't rotate it. Okay, that's fine. Essentially, the so the Weil spinner, the Weil equation has a set of matrices incorporated into it. So each x, so each real coordinate that has its derivative in a Weil equation, the derivative of that is then projected onto a two-component spinner. Not two. It would be a it's just projected onto a spinner, but obviously the so you take the derivative of your two-component Weil spinner with respect to a real spatial coordinate, right? And then you have what's called the Pauli matrices, which form a basis space in the just just the regular imaginary plane. So it's just it would be a basis space for a two-component imaginary vector space. Um, um, and it's these Pauli matrices that are responsible for the spin of the Weil equation being dependent on its handedness. And that's because the Pauli matrices, firstly, they mix the left and right-handed. They mix the two components, so they swap the components of the Weil spinner. As in, obviously, if you have the identity matrix right one's down the middle, then you have the opposite of the transpose of the identity matrix. The transpose of the identity matrix swaps the two vector terms, right? The Pauli matrices essentially include that in their capabilities. Um, so they simultaneously swap the components, and they add a phase shift, or at least in some of them, one of them adds a phase shift of 90 degrees. So you swap it and you add a phase shift of 90 degrees, which results in the two component spinner spinning in the opposite direction, essentially. But obviously, if you switch the from a left-handed to a right-handed Weil equation, you're adding a minus sign to your Pauli matrices, which then adds a minus sign to the direction of the phase shift, basically. Is, I believe, correct. Take it with a pinch of salt. If I keep saying it loud enough and long enough, it will be true. Right, so clearly I need to focus on building the computer a bit more. If you're wondering, actual quantum field theory describes fermions using the Dirac equation, which is a pair. It's a left and right-handed. It's a pair of left and right-handed Weyl equations with associated Weyl spins, but then the inclusion of a mass term. So the Dirac equation describes uh, essentially a four-component bispinner. So two component spinners with a mass, and I believe it is correct to say that would describe, for example, electrons, um, presumably quarks. Although obviously quarks have got the whole strong force going on, so it's like they're not going to be um, really free. I guess. I guess like the nucleons. Um, I'm not sure what the correct treatment of a nucleon is. But I'm assuming you would use the regular sort of wave equation for it. Although obviously, when propagating in free space, I mean when it's bound in a nucleus, I think it's an entirely different proposition really. But obviously, this is just for fermions. This is the spin half-world particles, which are described by spinners, which are complex vectors. And obviously, complex vectors don't complex vectors because the imaginary axis gives them an internal degree of freedom. When you apply rotations to complex vectors, so for example, if you rotate the space they're embedded in, the space is a real space, and you rotate the real space by 360 degrees. The complex vector will have been rotated by 180 degrees. Well, the way to visualize this is to visualize that the complex vector is essentially twisted in the imaginary axis. So if you imagine it's 2D plane and its complex vector is two component complex vector, the top complex vector will have twisted. It's like a Mobius band essentially. If you know those little strips that have one side because you've twisted them in the middle, so that there's only one side. If you follow around on one side, you end up on the other side. Essentially, the complex vector will describe a Mobius band in the complex plane, whilst it's being rotated in the real plane, which means it has, well, at least a bunch of useful properties. But that's the sort of basic gist of it, and that's what's meant by spin half, basically, which is somewhat of a mysterious property when you apply it to actual particles. It's like it's not really amenable to a physical explanation for why that is the case, other than saying that the particle probably has some internal degrees of freedom that lead to that. Well, I think some people argue it's because of relativistic effects. But also, obviously, it is observable and it has very very real effects for the particle's behavior, right? So, spin half particles which we call fermions, have a very specific behavior when they are essentially shoved together. Let's say, like a spin half particle will be. So, well, there's a thing called Fermi. It's Fermi-Dirac statistics. It could be Fermi-Pauli statistics. I can't remember. One of those two. Um, what this means is that spin half particles can't ever occupy the same quantum state because well, there's a Pauli exclusion principle which says why. It's a pretty simple bit of math, but I'm not going to reiterate it here. But essentially, the way if you bring their quantum states if their quantum states get close, they can never. They essentially, well, they experience, I think, what's really phrased as degeneracy pressure, sort of pseudo force, um, which basically means they can never stack up on top of each other, which is an interesting thing for black holes and neutron stars, because in theory, at least, the black hole, the singularity of the black hole should be strong enough on paper to crush spin half particles into each other somehow. And it's like, what does that mean? Who knows? And I think, like, neutron stars, I think, are specifically held up by this degeneracy pressure, right? They don't. Neutron stars don't collapse into themselves because they are essentially sitting on top of the Pauli exclusion principle. Um, Whereas the opposite of this is true for bosons, which are the integer spin particles. So these have spin 1 through -1, and also if the graviton exists, the graviton has a spin of 2, for reasons which are not currently apparent to myself, although apparently it's fairly obvious. Um, so graviton, the graviton is not the graviton, but the point is bosons. Bosons have the opposite effect, where there's essentially a slight statistical. It's slightly statistically more likely that you'll find them sitting on top of each other. So essentially, you can stack an infinite number of photons into any one quantum state. So a good example of thinking about a good example of spin is the obvious one, right? Electrons and electron orbitals, right? Electron orbitals only exist because you can only put a finite number of electrons in any given electron state, at any given orbital state, right? So the ground state has two distinct wave functions that can sit in it, right? So that's why you have two electrons in the ground state. Then the states above that have slightly more different combinations of electron wave function. Therefore, you have more electron waves in there that are discrete states, and they aren't electrons existing in the same state, and that's why there are limits to how many electrons can sit in each orbital. Although presumably, if there was no limit, then the atom would just explode because of the electrostatic force. But like, if you could just stack an infinite number of electrons in the ground state, I think that would presumably that would ruin physics. But yes. So sorry, it's just I just want to. It's sort of helpful to talk about complicated concepts like this as sort of revision. And it's like I figured I'm doing the streams. I should do a sort of dear diary. But like 890 apparently. Ay ay ay. How to write. Sorry about that. That's just, yeah. Sometimes the old figures don't do what you need them to do. So yes, this is So if you're wondering what I'm doing right now, I am. So the the multiplier, which is this number on the side here, um, it governs which bit shifted versions of the multiplicand, which is that number there, get through to the binary adder over there. So if there's a 1 in this number over here, that layer needs to come around here and it needs to switch on this bit shifted number over here, allow it through to the addition, right? Because essentially you bit shift the one number based on the powers of 2 in the other number, and then you sum the result. Is, I believe, correct. So yeah, just got to fill this out. A bit dull, really. This whole section has been kind of dull. Ay. Doesn't help that I'm sitting in a dark room and my keyboard is not backlit. Oh yes, that's the other thing. I looked up what the correct term was for the multiplier and the multiplicand in a multiplication equation. And it's just multiplier and multiplicand. Obviously, because the multiplication is commutative, you can switch the two around arbitrarily. But the multiplicand is the thing that you think of as being multiplied by the multiplier. So it's a slight psychological difference, essentially. You see, final, second to last one. Bit shift of just 1. Each one of those lines gets sent up 1, and then a 0 gets added at the bottom, although don't need to add a 0 at the bottom because it doesn't matter. Once it gets fed into the adder, the adder doesn't care that there's no input at the bottom. Just check dropped frames. I've been having some internet. Yeah, that's the other thing. I had some, which I discussed last stream, was I had some internet dropout issues. Specifically last week now. That's why there's a couple of streams on the channel that were 20 seconds long. Whatever that seems to have been not local to my connection, so it's fixed now. Didn't have to get on to anybody about it. And as always, if there is anybody in the chat, thanks for watching, but I don't have a second monitor, so I'm not checking chat. Convenient. Once I'm done with this, I need to come back and make sure all of these are working as intended as well. So, but for now, I'm just filling in the main insta wires. Yes. Right, excuse me. Sorry, it's maundering under my breath. um, excuse me. Right. Yeah, it's just got to get this done basically. Um, when it's done, um, it'll be a quick job to put in all of the binary adders. In reality, it's all nearly done, isn't it? It's close to. I suppose once I've done multiplication, I'm gonna have to figure out how division works. I'm gonna have to figure out how floating points work. So I suppose I'm gonna need floating points and signed integers. Now I actually might have to look that up. I might not be smart enough to figure that out on my own, you know. It's a bit egotistical, but it is what it is. Um, I mean, I wanna see if I can figure out floating points. I think I can handle on my own. Signed integers is maybe a little bit more difficult, oddly enough. So, for example, I think the floating points. Well, so I think what I actually will do is I'll have fixed points to make it more simple because none of this infrastructure is really suited for um, singling out the so a floating point. For those of you who aren't computer literate, floating point is computer science term for a number with a decimal point in it. So it's 0.0 whatever is a floating point number basically. Well, floating point specifically does. Um, well, what floating point means is that you have a second number attached to the main number, and the second number tells you the position of the floating point in the first number. If I remember my computer science correctly, it's been a while. Maybe wrong. I think it's correct. Either way, the general gist of it is that you have um, one number containing the decimal number, as in a number with a decimal point in it, and then you have a secondary number riding sidecar rather, not side saddle. That's something else. Riding sidecar that denotes where the decimal point should be placed in the other number. So if you have a 16-bit number, right, you would need 4 bits dedicated to demarcate the location of the floating point in that 16-bit number. Um, since this computer is very slow with its memory read writes, and I don't have the capacity to I want to save on the instruction set as much as possible. So if I just use fixed point numbers, I think I can get away with putting the fixed point numbers through same binary adder, for example, as the integer numbers. Which will save one instruction, because obviously instructions currently are limited to 4 bits. So I've only got 16 available instructions, right? It's a very small instruction set. And I'm almost sure at this point that I'm going to have to double it to 32, so add an extra bit in. But obviously the point of it is that that goes back to some very specific architectural decisions I made about the way instructions are stored in memory. But either way, it's like to be instruction efficient. I think fixed. If I have fixed point decimal numbers, that might work better. Um, unsigned integers. Sorry, all the integers are right now unsigned. Signed integers. So the one thing you can do is you can keep track of signed integers just manually using. So, for example, in the coding itself, if you're a clever coder, you should be able to keep track of which integers are signed and unsigned. It's just a question of figuring out how the subtraction works, I guess. So it's a little bit more complicated, and I don't have a pretty good idea of how I'm going to do it. Obviously, the architecture of this thing is because it takes so long to load an instruction from memory, right? I want the instructions. Obviously, there's going to be a program sitting in memory, and the program is going to be a list of instructions in sequential order, right? And obviously, one memory address is 16 bits, so this is a 16-bit system, and each memory address has 16 bits in it. As of right now, the instruction set is 4 bits long, and the memory address set is 12 bits long. Obviously, 12 plus 4 is 16. So what that means is I can have one instruction stored in a memory address, and in the same memory address, I can have memory address stored in it. So I can have an instruction and an associated memory address. What this means is I can store an instruction for, let's say, binary addition. I can have an instruction that says take the number at memory address X and deliver it to the binary adder, right? Because of the way the binary adder works, the binary adder doesn't need to be told to do the addition. It'll just do the addition once it's received two numbers. But I do need an instruction that says either. Actually, I don't even need an instruction that says whether it's a read or write or not, because the binary adder stores that information on its own. Oh bother, this is going to be complicated, isn't it? Could be some complications with this going forwards that I've not taken into account. Oh well, I'll deal with it later. Just for now, just get it built. If you don't know, Insta-wires get a little bit broken when they have redstone signals running around them which aren't on their line. So, for example, this redstone signal coming over the top here could cause an issue. Yeah, so I'll fill all these out and I'll readjust that afterwards. Is that everything done? No, this one needs doing. Any other ones? That needs doing. Obviously, with the instruction set, every bit I add to the instruction set is a bit I have to take away from the total memory address space. Although there may be workarounds for that. Slow workarounds, but workarounds nonetheless. So if I have a 5-bit CPU instruction set, then that means I have 11 bits available for memory address. Which halves the size of my memory address, and it doubles the size of my. I go from 16 instructions to 32 instructions, which should be enough as like it's not going to be a super complicated computer. I think that's all of them, isn't it? So what I need to do is I need to extend all of these out, figure out where there's going to be overlap, what's going to be broken. That should be okay. Yes, that's well, it just needs to be long enough to be able to see what's overlapping and what's not. Excuse me. I need a name for the architecture of this computer, and it needs to be suitably spooky. Like the overall computer is called the Bureau, but it's what architecture is it running on? Or like the Timberwind architecture or something like that. Like vaguely Intel sounding. It's Timberwind, I think, was the atomic tests in the South Pacific. So it's obviously a bit sinister, to put it mildly. Yeah, it's probably going to be broken, isn't it? That'll certainly be broken. Can't really move it forward, so well, I'll deal with it. I might even deal with it tomorrow, to be honest. Getting tired now. I'll probably log off soon. It's getting dark early, man. There's a reference for somebody. course, doing this will ruin the nice staggered look it had, but it was inevitable, so. Yeah, that's going to be broken. This one's going to be broken. Brethren, it's like brethren. Excuse my maundering. Um, I've been live for exactly, well, not exactly, but almost exactly an hour. Oh, and you know what I forgot? I forgot the red bit, the trailing bit. I forgot to do that. It can wait till tomorrow. Thanks for watching, and good night. And don't forget to like and subscribe.